it rolling. So 2.5 is applications of right triangles. In 2.4, we actually did application problems. We finished off that section solving problems, but today we're going to talk a little bit about bearing, and that's a different kind of problem. And so we're going to do 3 examples of bearing problems that you're going to see come up. So what is bearing? Well, bearing is the direction of a motion that the object is taking, or it can be thought of as the direction of a second object at a distance relative to the first object. So when we talk about getting our bearings, that's actually what we're talking about. We're trying to figure out which way we're facing, where we're at, our location. That's where that saying comes from, is it comes from the actual mathematical getting your bearings. And so if we're talking about a stationary object, we might talk about the direction that it's traveling in. Oftentimes it's a boat or a plane. Or we could talk about 2 different objects in reference to each other, is how that this is going to play out. And bearing, unfortunately, is different than just looking at our traditional angles. It's different in that we're always going to start from a north direction. So this is bearing, this is going to have directions in it, and if you were directionally challenged like I am, it's not as bad as like somebody telling you go east and west, because you're always going to start from a north direction, a north starting point. And so there's 2 different ways we're going to talk about expressing bearing, and the first one is on the front of this paper right here, where it says when a single angle is given, it is understood that the bearing is measured clockwise direction from due north. And that's where this is different than all the other trig that we've done so far, because all the other trig, we start over here at our x-axis, and then we go counterclockwise. With bearing, you're going to start from a north, which is like the 90 degree, your y-axis, and you're going to go clockwise. So you're going in the opposite direction that you've been used to going. So that takes a little bit of getting used to. Luckily, we don't do a ton of bearing problems, but you do have to do that. So there's an example of all 3 different styles of angles that you could come up with a north bearing, where we have an acute angle, we have an obtuse angle, and then we have one greater than 180 and one greater than 270, and how that's going to be reflected, because we're starting with our initial side on the y-axis and then going clockwise around. Any questions on that? It's backwards on what we were doing, I know. Okay. Those are the notes. There's one other little section of notes on the next page, but that's really the notes that are necessary for this first problem. And really, when it comes down to almost any problem you encounter in this class, the majority of the work actually comes from being able to read the words and being able to decipher it and draw a picture. So I feel like that's the hardest thing, and once you get the picture drawn, the trig that comes out of it isn't as bad as all the words make it look. So it says we are dealing with radar stations, so think about like radar towers out, you know, like when you drive by. It says radar stations A and B are on an east-west line, 3.7 kilometers apart. So thinking about the fact that, bless you, that we are always starting from a north direction, east and west then is going to lie on our x-axis. It's horizontal. Okay? So what they just told me is that we have station A, and then directly horizontally we have station B, because they are east and west of each other. And something that I like to do just to get my bearings is I draw in the north side of my angles with dashed lines so I know where my bearing is, where I'm starting from, where my initial sides for these different angles are going to come from. It told me I'm 3.7 kilometers away. It says that station A detects a plane at point C with a bearing of 61 degrees. So I'm going to put a random dot out here that represents my plane. And I'm going to connect my dots, because then it says station B simultaneously detects the same plane at a bearing of 331 degrees. So both these towers are detecting the exact same plane at the exact same moment. and thus we're getting a triangle out of this. But they gave us the different bearings with our angles, and it said station A detects that with a bearing of 61 degrees. Now, we may look at this and say, okay, well, we just drew in a triangle, so right here, angle A is 61 degrees, and that's what I want to do. But that's not what bearing is telling us. Remember, bearing starts at the north, and then we go clockwise however many degrees it's telling us to go. So that's why I drew in this north side, because we're going to start here, and then we have to move 61 degrees before we hit this side of our triangle. That means this is actually the angle that's 61 degrees. Not the one inside the triangle, but the one outside of the triangle. Because that's a bearing angle. We're going from north and we're going clockwise 61 degrees. Now for station B, we start from the north and we go clockwise 331 degrees. So that's going to look something like this last example over here on the far right, where we're going all the way around until we hit that side of our triangle. That's 331 degrees. Now, something we need to recognize real quick. Look at this north bearing line and look at my east-west line. What kind of angle does that make? Yeah, this makes a right angle in here. That means that's 90 degrees, isn't it? So if we were thinking about our Cartesian coordinate system and we think about moving in the opposite direction, every time we change quadrants, we move 90 degrees. Yeah? And so what we've actually done is we've gone all the way around. We went through 90, we went through 180, we went through this horizontal line is actually like our 270, and then we went a little bit further. So we can figure out what that little bit further is by taking, let me write, measure of angle B is going to be 331 degrees, take away the 270. Because what we're doing is we're finding our reference angle. And that's going to be what the measure of angle B is, which is not something it asks for, but in order to find out how far away A is from C, we're going to have to find out other information. And so we find out that the measure of angle B is 61 degrees. So that's inside the triangle. Who wants to take a stab at what the measure of angle A is? That's this other one over here. It is going to be 90 minus 61 because once again, our north line and our horizontal east-west line is going to give us a right angle over here. Which means if we take 90 degrees and we minus the 61 degrees, we'll find the measure of angle A, which is 29 degrees. And you're like, okay, that's great. We need to figure out one more angle, just so that we know what kind of math or trig we can use here. What do we know about the measure of the interior angles? What do they have to add up to be? 180. What does 29 and 61 add up to? Yeah, it adds up to 90. So if these two angles add up to 90, then what's the measure of angle C? Yeah, it's also 90. We have a right triangle. That's really good for us because now we can use all of our traditional trig that we know. What we're trying to find out is it says find the distance from A to the plane, which is at C. We're trying to find out this side of this triangle. And I'm labeling it B because we learned on Wednesday that the sides opposite the angles, you label them with the lowercase letters. So I'm trying to find the measure of angle B. So now that I know all of my angles and I know that my hypotenuse is 3.7, how can I find the measure of side B? Of what? That's right. We can take sine of 61 degrees. Sine is going to be opposite over hypotenuse, so that'll be b over the hypotenuse, which is 3.7. So we can take 3.7 times sine of 61 degrees, and that'll tell us what b is. Or you could do the exact same process, but we could use the angle of 29 degrees. And if we're using the angle of 29 degrees, then we're not using opposite, we're using adjacent over hypotenuse. And if we're using adjacent over hypotenuse, what trig function is that? Yeah, that's cosine. So this is an or situation. Either of these are going to give you the exact same measurement. If you type those bad boys into your calculator, either one of them, you should get 3.2 kilometers. Oops, sorry, I moved. So the trig itself is not exceptionally difficult, but making sure that we draw our picture correctly and then deduce the information that they want us to get out of it, that can be where it's difficult, especially with bearing, because like I said, we're used to going counterclockwise. We're used to starting at our initial side on that x-axis, and that's not how we're going to do it with bearing. We have to start northward, and then we go clockwise around to figure out what those different bearing degrees are. Are there any questions on this one? Okay. Let me see. How bad can you see through that? Pretty bad. I'm going to go get a fresh one. Just always take my having to do the worksheets up there so that I don't have to go get another one. Okay, so I told you there was two different ways to do bearing, and here's the other method. The other method is where you start with a north-south line and you use an acute angle to show the direction, whether east or west from that line. This is how ships and planes, this is how we talk about the latitude and longitude, is with this, where we talk about going, east from north, where we have north 42 degrees east. And what that means is we start from the north and we're going to travel to the east or to the right 42 degrees. Notice that the opposite of that, we would travel west from the northern position. And if we're traveling from the southern position, if we travel east, we travel right. And if we travel west, we travel left. So if you are ever told whether north or south and your bearing is going to be east, you're going to move to the right. And if you are traveling west, either north or south, you're going to move to the left. And so this one's slightly different in how we're going to use our calculations. Again, the math isn't going to be horrible. It's making sure we draw our picture correctly. Because this time we have a ship. And our good old ship is leaving the port, and it sails on a bearing of north 47 degrees east. Okay? So I'm going to go ahead and draw in my north-south line to give me kind of a good starting point to get my bearings as it would be. North, south. And it says I'm starting from north and I'm traveling 47 degrees east. So that's going to be like this first example where I'm starting from the north, I'm going clockwise 47 degrees. So here's my ship. And I'm going to draw it out here, and this is 47 degrees. That's what I know. And it travels east for 3.5 miles. That's great. It doesn't really matter at this point. So I'm going to call this A. It then turns and sails on a bearing of south 43 degrees east for 4 hours. So I'm going to turn my ship a different direction, so I'm going to have a new bearing. So I'm going to draw in another north-south line to go off of. Because in this case, I'm going off of my south, but I'm going east again. So I'm going to go this direction. I'm going to move to the right. And how far am I moving to the right? Well, I'm going to move 43 degrees to the right. So the way you draw your triangle doesn't really matter so much. It just matters that you label the right sections. If the ship's rate is 22 knots, which are nautical miles per hour, find the distance of the ship from its port to where it ended after it went that second amount of time. So we want to know how far apart is A from B. So I'm going to call that C because it's right across from side C, or you could call it X. In my notes, I called it X, whichever one is less confusing to you. But this is what we want to find. How far away is our starting point from where that ship stopped moving? And you're like, okay, well, once again, we have lots of information, and none of it seems super duper helpful just yet. But they actually gave you everything that you need, because as the ship travels from point A to where it's going to turn up here at point C, we know that it traveled for 3.5 hours, yeah? And they even told us what the speed is. It's 22 knots. So I'm going to take 3.5 hours times the 22 in order to figure out how far the ship actually traveled at that point. And if you do that, you get 77 nautical miles. That means that the side from A to C is 77 miles, or nautical miles, however you want to think about it. But at that point, after it went 77 nautical miles, it turned. And after it turned, it went from C to B. And when it went from C to B, it traveled for 4 hours, again at the same speed. So, I mean, that ship's pretty agile in that it can turn and never has to stop in order to slow down and to do this radical turn. So you take 4 times 22 and you get 88 nautical miles. Okay, so what do you think we should do now? We know what sides B and A are theoretically. We don't know what side C is. We also don't know what kind of triangle we have just yet. We don't know if this is a 90-degree triangle. If it is, if this is a right triangle, then we can use Pythagorean theorem and figure out what C is pretty well. So in order to figure out if we have a right triangle, we need to figure out what the measures of these inside angles are. The easiest thing to figure out, actually, is this little bit right here. Because remember that 43 degrees is only from this side over until our north line. So we really have this other small angle in here, and we need to figure out what it is. So something I want you to notice, though, is when we drew these two north-south lines in here, we drew parallel lines, yeah? And this side of our triangle cuts it like a transversal. We just tested over this on Monday. And so if we're looking at this, we have alternating interior angles, and that means they're the same. That means 47 degrees is what this little flower is right here. And 47 plus 43 is what? 90 degrees. So in my notes, I give a little bit more. I'm going to show you. Like on this page that I scanned in, I tell you that the measure of the star angle is 47 degrees because of the alternating interior angles of the transversal. If you ever see me write these 3 little dots that are in the triangle shape, that means therefore. So the measure of angle C is 90 degrees. And as soon as we know that the measure of angle C is 90 degrees, we don't actually have to know what the measure of angle A or B are. What we have found out is we're dealing with a right triangle. And if we're dealing with a right triangle, we can do Pythagorean's theorem. We know 2 side lengths. We can use that to find our third side length. Because Pythagorean theorem says a squared plus b squared equals c squared. A is 88 squared plus 77 squared. Does it matter which order you write those in? No, it does not. 7744 plus 5929 And you type all of that in, and we find that C is approximately 116.9 nautical miles. So sometimes you're going to have to use, like on our first example, we had to know all of our angles because then we used our trigonometric functions, our sine or our cosine, in order to find out the length of the side of the triangle. Other times, they're going to give you enough information that you're going to be able to come up with what the side lengths are, and then you would either have to figure out what an angle is, or you'd figure out what the third side length is, like on this example. Drawing those north-south bearing lines, I think, are very helpful. Again, you're going to do as much as you need to do. So if you don't need a super complex picture or one with all this information on it, you don't have to draw that. You can do it however you like to do it. I do say, though, that you probably need at least some picture as you work through these problems. Are there any questions at all on those first two? All right, then let's move on to our last example. This one came with a picture, so there's no questioning, oh no, there we go, what the problem is asking us, or at least showing us, because they gave us a nice tree picture. And it says, not San Francisco, just Francisco, needs to know the height of this tree. And so from a given point on the ground, he finds that the angle of elevation to the top of the tree is 36.7 degrees. That's the smaller inside triangle right here. Then he moves back 50 feet, and then from that second point, the angle of elevation to the top of the tree is 22.2 degrees. So let's find the height of the tree. Okay, so what I'm going to do, because I think it's more helpful than like dealing with each of these separately or together in one picture, I'm going to draw these triangles over to the side. So that smaller triangle, the first one that he made, I'm going to draw over here completely by itself, because that's going to help me just to isolate that one triangle where this is our side H, this is our side X, this is 36.7 degrees. And then I'm going to do the same thing for our larger triangle, which I'm going to have be green. If you're colorblind, I'm sorry, I'll make it bigger and below. Look at this. Again, this side is still H because we're still using the tree as our reference. But what's changed is our base has gone from X to 50 plus X because we went an additional 50 feet. And our inside angle has changed to 22.2 degrees. And you're like, okay. So now we have two triangles, and we have two different things we don't know. We don't know X, and we don't know H. So really what we're kind of doing is almost like a systems of equations problem in a trig class. Since I'm trying to figure out what H is, I'm going to use both these triangles to get me some kind of an equation set equal to H. And here's what I mean by that. If I look at this information on this green triangle, I have an angle, and I have the side that's opposite that angle, and I have the side that is adjacent to that angle. So which of my trig functions should I use if I have the opposite and the adjacent side? Yeah, I can use tangent. If I do tangent of 22.2 degrees, that's going to be the opposite, which is H, over the adjacent, which is 50 plus X. Since I want to know what H is, I'm going to move that 50 plus X over, and I'm going to leave it in a set of parentheses so that I don't forget that this is actually multiplying against this tangent. Now I'm going to do the exact same process with the red triangle, with this other triangle that's up here. I can find tangent of 36.7 degrees is the height over x, so multiply that x over. Now I have two different equations that are set equal to the exact same thing. The green equation is equal to h, the red equation is equal to h. Since they're both equal to the same thing, I can set them equal to each other. To where I have, let's see, how much space do I need? I'm going to come down here. I'm going to have 50 plus x times tangent 22.2 equals x times tangent of 36.7. And here's something I'm going to go ahead and warn you about is, could you type in tangent of 22.2 in your calculator and come up with a decimal out of the gate? You sure can. But then you're going to write that decimal over and over and over again. And the fact is that you're then going to multiply that by the 50 here in a minute. And you've probably done some rounding, and the more that you round, the further from the true answer you're going to get. So I recommend leaving it in the long form as long as possible until the very last step, and then typing it all into your calculator then. That way you get the most accurate answer at the end. Because what I'm going to do now is I have to distribute this tangent 22.2 to the x and to the 50. So I have 50 times tangent 22.2 plus x times tangent 22.2 equals x times tangent 36.7. You're like, well, this looks gross. I know it does. But this is the algebra part of the trig. So I have, this is all numbers, this first section, 50 tangent 22.2. But then I have an x tangent 22.2, and on the other side I have x tangent of 36.7. If we were trying to solve this as a regular equation, we'd get everything with an x on one side. So I'm going to subtract this x tangent 22.2 over to the other side. Because now, if I look at my two terms on the right-hand side, I have x tangent 36.7 minus x tangent 22.2. If I had 3x plus, plus is fine, 5x, I could add those together, right? Or I could also think about factoring out that x, which is what I need to do here because what's inside my tangents are not the same. So I'm going to factor the x out so that I can divide here in just a minute. Because now in order to solve for x, that x is multiplying against everything inside these parentheses, so I'm going to divide that set of parentheses over to where I have 50 tangent 22.2 all over this tangent 36.7 minus tangent 22.2, and that equals x. And you're like, well, that is a lot of stuff. And here's the great thing. That's not even what you're looking for. That tells you x. X is how far Francisco walked away from the tree. That's not actually the height of the tree. But that's okay, because we have this equation where x times the tangent of 36.7, that equals h. So if we take all of this bad boy that we just got, this big old gross thing, and we take that times, sorry, I can't talk and write at the same time. If we take that times the tangent of 36.7, then we're going to have what h is. Don't try and do magic math where you're like, well, I have a tangent 36.7 and tangent 36.7. Obviously, I can cancel it out. That's magic math. It will be wrong. Your calculators can handle this. Depending on what style calculator you have, you may have to do it in different parts. You may have to calculate what 50 tangent 22.2 is first, and then divide that by the tangent 36.7 minus tangent 22.2. But even my old school calculator from the early 2000s or whenever I got it, this little Texas Instrument, it would handle this style of problem. And actually I could type it all in straight out of the gate with just this one. So this can handle it. Your other ones can handle it as well. if you type all of that in, you find that the height of the tree is approximately 45 feet. And it said, find the height of the tree to the nearest foot in our problem. So we are going to round it. So this problem, even though it's a trig problem, actually has a lot more to do with algebra. A lot of the stuff that you learned in Math 20, 30, college algebra, whatever kind of math you took before this class. Because what we're doing is we have two equations, two unknowns, which is the systems of equations, so we set them equal to each other. Then we have to do all this algebra in order to get x by itself, but x wasn't what we were actually wanted in the end. So then we had to do a substitution and plug it back into our equation to actually solve for the height of the tree. In terms of algebra, this is probably the most algebra-intensive problem that you will encounter. Are there any questions on this one or on any of the other two bearing problems that we did earlier?